Very basics of antideriving is understanding that antideriving is the inverse of deriving. Similar to how multiplication and division are inverses, they undo each other, and how addition and subtraction undo each other, so does antideriving and deriving. For example, if we derive x, the derivative of x is just equal to 1. But if we do the integral of 1, then we just get x plus c. Now, there are some things that you will be required to simply just know when antideriving indefinite integrals, and that is your properties. So some of your basic properties are that you can take out a constant. So for example, the integral of k of some function, I will say a function t, is just simply equal to k of the integral of f of t. Now you would antiderive as normal and then proceed to distribute the constant out to everything. For example, if you have, let's say the function of t is equal to x squared plus 1. All right, it's meant to be a t squared plus 1. And then our k value is equal to 5. And we have the integral of 5 of t squared plus 1. Now, you could also just distribute this 5 out into the t squared plus 5, but you could also just factor it out, as we've seen in the property. Factor it out. And you're left with t squared plus 1 dt. And then the 5 will continue to follow, and then we antiderive. We'll get more in depth into the anti-power rules and how you can antiderive, but just understand that this will be distributed. Right, and then from this point on, you would distribute. So you get 5t cubed over 3 plus 5t plus c. Another integral property that you should know is that you can separate your integrals. So as we previously saw in the previous example where we had t squared plus 1 dt, right? We can also just distribute this integral, treating it as it's also almost as if it's a constant that's multiplying throughout. So we can just distribute that integral to t squared, and we see a plus, so we're going to do plus the integral of 1, and then don't forget dt. Right, so then now we just have to focus on 1. So the integral of t squared is simply t cubed over 3, and the integral of 1 is just t. And then this would be plus, and we only need one c, because although we are taking an integral twice, but because there's addition, we only need one constant. Now there's a crucial part into knowing how to antiderive, and that is knowing your anti-power rule. So as you recall when we were doing derivatives, the derivatives of x is simply xn minus 1 times n. While when you're doing your integrals, you're doing the opposite of each side. So similar how we're doing, or opposite of how we're doing subtraction, we'll be doing multiplication, addition, and how we are doing multiplication here, we'll be doing division. So when you do the integral of x, you're going to be adding the exponent by 1 and dividing the whole thing by the exponent plus 1. So, for example, if you have the integral of x cubed, we're going to add 1 to the exponent, and then this will give us 4, right? So then we have x to the power 4 divided by 4. And you can always verify that this is correct by taking the derivative of this. So we do the derivative of x to the power 4 over 4, and we get 4x cubed over 4. The 4's cancel out, and we're left with x cubed. We can see the same. However, there's one exception to anti-power rule, and that is when x is to the power of negative 1. Because when you have the integral of x negative 1, that is the same as the integral of 1 over x, which, as you recall, back when we were doing derivatives, the derivative of your natural log of x was equal to 1 over x. So we can't apply anti-power rule in this case. You just have to understand that when you have a negative 1 exponent, that will just be equal to your natural log. So this is just natural log of x plus c. Some other properties that are very crucial when finding antiderivatives, and this will require a lot more memorization, especially when you get into your inverse trig functions. But uh, for this video, we'll only focus on the basic trigonometric functions. So I'll write them all down and then describe and then tell you how each derivative gets you back to the integral. It sounds confusing, but let me write it all. Now that you look at the trigonometric formulas, you may notice a pattern. So when you look at the right side of the equation, you'll see that when you do the derivative of the right side equation, you'll get the function inside the integral. So the derivative of sine is cosine, derivative of tangent is secant squared, derivative of secant is secant times tangent. And when you do the derivative of cosine, you get negative sine. But we attach this negative because inside this function is positive sine. So negative times negative sine gives you positive sine. And that applies to all these cases, right? So then the derivative of cotangent would give you negative cosecant squared, but because we have that negative, this is positive. Derivative of cosecant is negative cosecant times cotangent, but again, a negative. Now, you don't have to memorize anything new here. When you were doing derivatives, you should have already understood the derivatives of your trigonometric functions. So it's just going backwards. It gets a little weird once you get into your inverse trigonometric functions because that would require substitution and recognizing when you have either an inverse sine or inverse cosine or inverse tangent function. But this is just the basic anti-derivatives, so you don't have to know that just yet. Now, there are some last few properties that you should know before we get into practice. And one of them is your exponents. So the integral of e to the x is just e to the x, because the derivative of e to the x is simply e to the x. So if you take the integral of e to the x, you'll still get e to the x. Another thing when you're solving or when you're anti-deriving functions is that you should always take your values out of a radical or out of the denominator. So for example, 1 over x cubed dx and the integral of square root of x dx. It's the same basic strategy when you were deriving. Is you don't want to take the derivative when a function value is in the denominator or when you have something contained within a radical, and you just simply rewrite it. So integral is minus dx. So although we have a negative exponent, our property specifically states that we have to have -1, so we can apply the specific property where the integral of x to the power -1 is simply the natural log of x. However, in this case, we don't have -1, we have -3. So we can apply the same basic power rules where we add 1 to the exponent and divide by the exponent plus 1, and we simply get x -2, -2, and then we can rewrite that as 1 over -2x squared. C. Now we do the same thing for this case. This is the integral of x over 1/2 dx, and apply the same anti-power rule. So we have x 1/2 plus 1, but we can rewrite 1 as 2 over 2. Doing this allows us to combine the exponents much easier. 1/2 plus 2 over 2, which is equal to x to the power of 3 over 2 over 3 over 2. Now, we would simply flip this, and this gives us 2 square root of x cubed plus c. So now that you know the necessary properties required for now, and the idea that you're basically applying the same strategies you've been applying for derivatives with integrals, but instead of doing them backwards, we can now move on to some practice. So let's do the integral of x to the power of 7 plus 2x cubed plus 4. Now, with one of your properties, you can distribute this integral all out. Right? So you could do the integral of x to the power of 7 dx plus the integral of 2x cubed dx plus the integral of 4 dx. You could do all of that. But when you're specifically taking exams, you're likely timed, and writing that integral all out takes a lot of time and doesn't optimize your time. So it is better just to understand that you are distributing this integral throughout everything, and you can just apply the anti-power rule to everything. So when we apply the anti-power rule to this first value, we get x 7 plus 1 over 7 plus 1. And then we do the same thing. So 2x cubed, we're simply plus 1 over 3 plus 1. And again here, plus 4. Now we can see that here we have no x value. So therefore you can think of this as x to the power of 0. Because x to the power of 0, or anything to the power of 0, we know is just 1. So we can rewrite that as that. So we have x 0 plus 1 over 0 plus 1 plus c. Now we would simplify this and get x to the power of 8 over 8 plus 2x fourth over 4 plus 4x power 1 over 1 plus c. Now, specifically for the AP calculus exam, you never have to simplify fractions. So although you could simplify this as x to the power of 4 over 2, rewriting that takes up just a small amount of time. It's insignificant, but it takes up time. So you don't have to rewrite this if you don't want to. This is an acceptable answer. More practice with constants. So 5, 4, and 32 dx dx. So as previously we mentioned, where we can imagine that there's a x to the power of 0 attached to all of these, we simply can just look at these and just know right away that when we apply the anti-power rule to the invisible x to the power of 0, it's just simply going to give us the constant times x. So we can know right away that this is 5x, 4x, 32x, right? Again, this can be written as the integral of 5x to the power of 0 times dx. So then in this case, we have 5x 0 plus 1 over 0 plus 1, which will just give us 5x1 over 1, which is just 5x. Now, never forget plus c when you're anti-deriving an indefinite integral. Plus c, plus c. The people that tend to get confused on is with constants, but specifically with the value of theta. And let me show you. So when you have, let's say, the integral of pi of d of theta, right? Understand that when you would do the derivative of pi, you could simply take it out and then do the derivative of the rest. Similar to how back when you think of related rates, when you would find the derivative of a specific volumetric function, you could factor out the radius and pi, and then do the derivative of everything else. Or no, you wouldn't be able to factor out radius. Typically, it would be like 1/4 or 3/4 and pi. And in this case, you can do the same thing, right? So this can be done as the integral of 1 d of theta of pi, right? So now, as we recalled with our properties of integrals, when we antiderive a constant, that would just be x. But in this case, we have to see what is right next to our value within the integral. And we see there's a theta. So we cannot write x or any other value but theta. So this would just be pi of theta plus c. Similar to this scenario, where as we know, e to the x of dx is simply just e to the x. But if we rewrite it as not as a function, but rather as a constant, so e of dt is not the same as just e. It is not. But rather, we can factor it out. We can take out the e, the integral of 1 dt. And as we saw, right, with our theta was previously here, now we have a value of t. So we do the same thing. So this is just e times t plus c. So understand that you have to look out for what value is to the right of d. So as we saw here, it was theta. Here it was t. In other cases, it will typically be x or y or some other value. Now this was where there was a lot of confusion, where I saw some people make a lot of mistakes. Now this was a problem where I saw a lot of people tend to get confused on. With trigonometric functions, I heavily recommend rewriting everything in terms of sine and cosine all the time. Similar to back in pre-calculus, it is recommended that you rewrite everything into sine and cosine so you can look at what things cancel out. So we can rewrite the integral and do sine of x, and then cotangent is simply cosine of x over sine of x, plus cosecant is the inverse of sine, so 1 over sine of x dx. And we can right away see that when we distribute the sine of x into each of these, the sine of x will cancel with the sine of x, and this will cancel with the sine of x. So then we're left with the integral of cosine of x plus 1 dx. Now, what function can we take the derivative to get cosine? And that is sine of x. And then 1 is simply the same as x to the power, or x to the power of 0, which again would just be x 0 plus 1, or 0 plus 1 plus c. Now, here's the problem where I saw some confusion, and it's not just because it's a trigonometric function, but because of the theta. Right. So again, whenever you have trigonometric functions, or you're dealing with trigonometric functions, I will always recommend to rewrite everything in terms of sine and cosine, similar to how back in pre-calculus, when you're doing identities of trigonometric functions, you rewrite everything into sine and cosine. You do the same here. So this integral is equal to sine of theta over 1 over sine of theta plus cosine of theta over sine of theta over d of theta. Now, when we distribute the sine of theta and see everything else, we can right away see that it cancels out with the denominators of everything within the inside. So the sine of theta cancels with that, sine of theta cancels with this. So we're just left with the integral of 1 plus cosine of theta of d of theta. Now, as we recall previously, 1 can be expressed as x to the power of 0, because x to the power of 0, or anything to the power of 0, is just 1. And when we apply the anti-power rule, we are just left with x plus sine of theta. We know that the derivative of sine is cosine. So therefore, when we do the integral of cosine, it's just sine plus c. However, there's one mistake here, and that is here we see that we have theta, and we don't have any x from the starting position. However, here we assumed that there was an x. So this is actually not correct. But the correct version is theta plus sine of theta plus c. Although that may look a little weird and unfamiliar, just seeing that theta isolated, it is what you would write, because x is not acceptable in this terms. Unless this was dx, then yes, but because we're given d of theta, we have to write theta. Same if it was any Greek letter or some other symbol, we would have to use this symbol as our quote-unquote x value. Now, understand when you're finding when you're anti-deriving indefinite integrals, specifically, understand that you will likely only see indefinite integrals on multiple choice. So just understand your properties and understand how to anti-derive, convert back to sine and cosine, take everything out from the denominator or any radicals, and if you're able to anti-derive quickly, then seeing these questions on MCQs won't be an issue. Your definite integrals are where it gets a little bit more complicated, just because it requires more meticulous work and being able to anti-derive and then plug in your interval. Those types of questions, when you are dealing with definite integrals, you will most likely see on FRQs and MCQs. But typically with definite integrals, they're the type of questions that you're glad to see on the MCQ, similar to how if you see a question that asks you to take the derivative of a basic function on the MCQ, you're just glad and you move on.